Good evening, everyone. Welcome to our series of video lessons for Unit 2. Unit 2 involves something called polynomials. And the idea behind this unit is it's an extension of the work that we did in Unit 1.5. So 1.5 was all about quadratics, and quadratics are x squared terms. So quadratics involve x squared kind of problems. So problems there you have like an x squared term, whether it's in factored form where you have maybe x and then x. So you have two separate factors, um, and they all form parabolographs. And they have very important specific properties, but one of those things is those properties are specific to quadratics. Um, but now what we're going to do is use the analytics that we use in quadratics, and we're going to try to apply them in a more general fashion to longer polynomials and learn how different operations that we can perform that are good for all types of expressions, not just ones with an x squared term. And that's what all of this is about. But we're going to start to kind of introduce this lesson is a little bit of an activity called Let's Make a Box. So, which box does not belong? All right, you know the drill here, folks. Each of these boxes could potentially have something a little different with it. So, what might be different? Okay, what jumps out at you? Well, first off, A has no picture associated with it. What else do we notice? This one here is in inches. So number C is inches, which actually inches are larger than centimeters. So this box may potentially be bigger than the others. This box is written with variables. All right. Now, next question. How do you find the volume of a box? Well, volume is length times width times height. And so for each of these boxes, we can find a volume, right? 4 times 8 times 10 is 320 centimeters cubed. And so for volume, we use cubic measurements. So cubic centimeters or cubic inches. Um, and that's, those are measurements that are pretty commonplace. So cc's, or cubic centimeters, um, is a small measurement. That's about, I think that's 1 milliliter, if I remember correctly. Um, 1 cubic centimeter is approximately 1 milliliter. Um, and 1 cubic inch, you might you might remember cubic inches from, I'm trying to think of a good one here. I've seen it before, and it's escaping me. Um, um, I think engine displacement is, I think, in cubic inches. But I think I think it differs on the type of engine. So there's some of them are measured in cubic inches and some are measured in cubic centimeters, and I think it depends on who makes it. Um, I believe so. Anyway, they're both a measure of volume. And so how about this box here? So this one, 16 times 10, this one's 160 centimeters cubed. This one is 320 inches cubed. Now, inches cubed, of course, is going to be much bigger since inches are bigger than centimeters. So this is actually the biggest box of all. Then you have this one here. So this box here is unique because it's written as an expression. Just because it's written in algebra, could we still find the volume of it? Well, yes. I mean, okay, sure, it tells you it's 320. But what if we didn't tell you that? What could you say? How could you represent the volume of this given that the sides are written with x's? Well, simply multiply them, right? And so you might have, x times x plus 1 times 4x equals 320. And so that expression can be used to represent the volume. And you could say V equals, or since we know the volume is 320, say it's equal to 320. Now, this is not going to follow the same properties as quadratics from our last unit because there's three factors um, rather than the usual two. So we do have to be a little bit careful with this, but um, can we figure out, we can't use the zero product property, that's for sure, but can we figure out what x has to be? Now, what are our choices? Well, I guess first thing we could do is we could just try a few numbers. Let's try 2. So if x is 2, what would it be? So if x is 2, you'd have 2, 3, and 8. And 2 times 3 is 6 times 8 is 48. No, that's not going to work. Okay, so x is not 2. So x is probably going to be higher than 2. Let's try 4. 4, 5, 4 times 4 is 16. 4 times 5 times 16 is 320. Okay, perfect. We did it. Not too hard to guess there. So x is 4. Okay, now, could we have found that a different way? Well, we could try using Desmos. Let's see how that would look. So let's pull up Desmos and let's actually type this in here. So we have x times x plus 1 times 4x. Oh, well, isn't that an interesting looking graph? It's like a parabola, but half of it's twisted. So it goes up and then down and then up again. Okay, and all right. So no, we could trace this up, but oh my goodness, don't we have to go to like 320 with this? Okay, so how about instead of saying equals 320, how about we subtract 320 from both sides, and then that way it equals 0, and now we're looking at the x-axis. And look, it crosses right at 4. So it looks like x was 4. And if we scroll way back, you can actually see down here, here is that line, again, right down here at negative 320. Okay, so there's that little double curve in the graph. Uh, so it turns out that um, these sorts of graphs, when they have three separate x's, it actually produces almost two separate curves instead of the one. It's like the graph now has three sections, an up, a down, and an up. And the more x's that you put into this, the more curves and bends and twists that these graphs could potentially have. Um, so kind of an interesting thought to kind of get you to where, um, eventually we're going to go this unit. And the higher the number of x's, um, the more complicated the graph is going to look. But they have similar properties. And there's some properties that they're shared among all those different polynomials and some that are unique. But for now, Desmos is probably our biggest tool involving that. Okay, let's take a look at a few more things, shall we? Let's go back to our slides and let's take a look. So the title of this lesson is called Building a Box. So let's actually try building a box. You may have done this in the past where you take a piece of paper and you cut a little square off of each corner. And so each of these side lengths here, each of these little pieces that we cut are all h. But for our purposes here, let's not call them x. Let's call them x, right, instead of h, because what we're going to do is try to model an expression from this. Okay, so let's call those x. And so you're cutting x by x squared from each side. And the question is going to be, well, what value of x is going to make the biggest box? So how does a box fold from this? You cut out the squares, and then what's going to be left is you're left with these tabs, okay? You're left with these tabs here, and then you fold these tabs. Again, if you picture like a dotted line, we'll just do it like this. And you picture a dotted line across here, right? And you fold this tab in, and you fold it up, and it's going to fold up into a box, and that's going to form the side of the box. Okay, so our next thing is we're going to be filling in a table, right? So let's say we have a nice big piece of paper. Um, One common size for a piece of paper that we can use is, um, now I could use a legal size paper. And let's do something with some numbers that make kind of sense a little bit here. So one common size of paper that we might find is um, 11 by 14. Um, 11 by 14 is like a kind of like a picture frame sort of size. So let's do that. Let's do 11. Let's see, don't need that. We'll do 11 and 14. And that's the total width of the whole side, okay? So actually what I'm going to do to make this a little bit easier, I'm going to put this here. I'm going to make this 14 and I'm going to make this 11. Okay, so here's my question. So if that's true, now I want you to picture in your mind that these sides fold up, okay? So if these sides fold up, what forms the length, the width, and the height, okay? So let's start with the length. Remember, these pieces are cut out. So when you fold this side up, the, these two corners are going to touch. And so because those are going to touch, and then these are going to touch, and then these are going to touch, and then these are going to touch. So what you'll have is this has to be the new length of the box. So how long is this piece here along the top before you get to the x's? Well, it's going to be 14, right? But you're cutting away an x on one side and an x on the other side. So this length here is 14 minus 2x. What if we cut the same thing on this side? Likewise, we have 11 total, but we're losing an x and we're losing an x here. So how much do we have here? We have 11 minus 2x. And then how tall is the actual box itself? So if these fold up 90 degrees, then the box is going to end up being x units tall. These line x's are going to touch each other, and so that's going to form straight up what the box is. So height equals x. Okay, so let's picture what happens, right, in each situation. So let's start, for instance, x is 1. Okay, so x is 1. We're going to cut 1 inch square out of each side. Okay, so if you cut 1 inch square from each side, how tall is this going to be here? Well, you lost an inch, you've lost an inch, so the length is going to be 12. On the side over here, you're going to have um, a lost an inch, so you're going to have 9. So let's fill that in on the chart here. Okay, so the square cutout is length 1, right? The length is going to end up being, again, you started with a 14, and we took 1 off of each side. So 14, 11, x. So what about the width? Again, you start with 11, you start with a width of 11 inches, but you're going to cut out 1 inch from each side, and so that leaves you with 9. And because the cutout is 1, that box will be 1 inch tall. So what's 12 times 9 times 1? 108 inches cubed. Okay, now what if instead we had a side length of 2? We took 2 inches square from each side. Okay, so if we took 2 inches square from each side, what do we have? We have 12, so we have 14, right? But we take 2 inches on the left and 2 inches on the right. So we've lost now 4 inches. This drops to 10. Now 11, we take 2 away, that's 9. 2 away, that's 7. And now the height is now 2. Okay, let's get rid of that little mark there. So 7, 2. And so what's 10 times 7 times 2? 140. Well, wouldn't you know, isn't that strange? We cut more sheet out from the box, and yet the box gets bigger. How interesting. What's next? Let's try 3. What if we do 3? Now, same idea, right? We start with 14, but we lose 3. We lose 3. This now drops to 8. You can see the pattern here. 11, we lose 3. We lose 3. That's now 5. And the box is now 3 inches tall. And 8 times 5 is 40, times 3 is 120. Now we're getting smaller again? Well, that's interesting. And one more for the record. If we did 4, you can see the pattern that's going to happen here. 12, 10, 8, that's now 6. We lost 2 more inches. We lost 2 more inches. Gain an inch here. And that's 72. You can see what's happening. Now, let's see, again, how this might look on Desmos. And so it's interesting for us to wonder about this. Is 2 the largest box that we can make? Looks like it, right? So let's go back to Desmos and let's actually do this out. So again, what was the length, the width, and the height? So the length was 14 minus 2x. The width was 11 minus 2x. And the height was just x. And so we have this expression here. And we have, oh, well, that's an interesting function. I can't really read that well, though. So I'm going to take the graph, and I'm going to expand it out a little bit. So we're going to take the x-axis. And I'm going to drop this down to maybe, let's do like, let's do like 3 to 5. Okay. Nope. Okay, that'll do. Okay. So here's the graph. Now I've expanded the x-axis and the y-axis out a little bit to make this graph kind of easy to see. Okay, so let's see what's happening. So it starts at 0, right? So remember x is the size of the square cutout. So if x is 0, our volume of the box is 0. Well, why is that? We haven't cut anything out. If we don't cut out a square, we can't make a box. And if x is 1, okay, here's 108, just like we predicted. Okay, and up here, here's 2. And at 2, we've got, scroll in a little bit there, about 140, which is what we pictured. Now here's something interesting. Look just beyond it. 2.039, 140.039. So it turns out we can actually make a very, very slightly larger box by using a number that's slightly larger than 2. I mean, in practice, is that really practical? No, it's not, but kind of interesting, right? Now, let's look at down here. What's also important are these other x-axes, x-intercepts, right? 5.5. Why at 5.5 do you also get a box length of 0, or box volume of 0? Well, it's because the width is 11. And when the width is 11, if you cut out 5.5 from either side, you're going to cut out the entire length or width of this box. And so you're not going to be able to make a box from that. You're just going to have a flat piece of paper. So the volume will be 0. Make sense? But then what's happening here? So here, why is this negative? So like for example, if x is 6, you get an answer of negative 12. Well, why? Because this function doesn't know that you're dealing with volume of like an actual box. It just plugs the numbers in. So if you were to plug 6 in for x, you would get 2, and then here you'd get a negative 1, and you'd get a 6. So 2 times negative 1 times 6 is negative 12. So you get a box with a negative volume, quote, quote, because one of the side lengths is negative. Can we have a box with negative dimensions? No. So, hey, look over here. What about this side? This end of the graph over here is like when you get past 7, what's happening? Like if I chose a square of size 8, you're getting something along 80. So does that mean if I cut out 8 inches square, I get a box of 80? And what if I chose 9? If I chose 9, I'd get a box size of 252, which is way bigger than 140. So that's good, right? Wrong, because as you can imagine, I can't cut out 9 inches square from this. What would happen? If I choose 9, what's happening is 2 of the side lengths are becoming negative, and negative times negative is positive. So this isn't actually a positive area or even one that's possible. It's just because the number itself happens to be positive. So the only number that makes sense is anything from 0 to 5.5. So this, I don't know if it won't let me write on there, but that happens to be the domain. So if I look at this graph here, so I can now say domain is x is less than 5.5, but is greater than 0. And we don't want to use equal to here because, again, I won't have a box at that point. So x can be some number that's in between 0 and 5.5. Now, one thing to point out is back in parabola time, you wanted to find the vertex. The vertex would have been halfway in between these two numbers, so 2.75. But notice that's not happening here. Notice this case, the vertex of this part of the graph, it's not 2.75, it's like 2.03. So our parabola tools won't work on a function like this, but the good news is we'll have other tools that will work. Now, when you have a situation like this, right, where you have, you're only interested in part of the graph, and that part of the graph has a maximum or a minimum, we call that a relative max, or in this case, a relative minimum. But the only one that's going to matter here is this, because my true box domain can only go from 0 to 5.5. In that area, there is a maximum. Is that the maximum of the whole function? No, because its maximum's way over here. But this doesn't matter to us because this doesn't make actual boxes. This part does. So we have to be, that's going to be one of the difficulties with this unit is, and working with polynomials, is that generally we're going to be looking at a section of the graph at a time and being able to look at properties of it rather than the whole entire graph. Although the whole entire graph will be useful to us in many other situations, um, but when we try to reference real life, sometimes we have to have a domain that's only a part. And then we can say what's the highest point, what's the lowest point in there. Okay? So let's take a look at a few things based on that. Okay, so again, here we just use decimals, so I'm not going to bother with that. Okay, So building the biggest box, right? We've already kind of done all this. So we've constructed the box. We wrote an expression. So just kind of clarify here, the way that this expression is going to look is v of x is equal to x times 11 minus 2x times 14 minus 2x. And you could put those in any order that you want, um, but that's one way of writing it. And we've already looked at this on graph and we've estimated what that point is. And that point is around 2 point, for this box, around 2.039. So let's write that in. Okay, now I specifically chose this to be different than the one I did in class, just so that there was another example out there of kind of how this works. In class, I used an 11 by 17 piece of paper to construct boxes because that's what I had available. But here I used 11 by 14. Okay, so x equals 2.039, and then volume is right around, it was like 140, right? 140.039? Yep, that makes sense. So 140.039. Again, not that much bigger than if we just used 2 inches. But hey, some problems are like that, some are not. Okay, all right, and we've already kind of talked over all of this. What is the range where x values are increasing, decreasing? Okay, so what's the value of x that doesn't make sense? Now, we've discussed lots of values, right? Say x equals 9, and the reason why is because you get 2 negative sides. But then this goes again. The domain of the function is 0 is less than x, less than 5.5. What's the smallest value that would work for x? The largest. Here you go. We've got our domain there. So this kind of um, fits into that. What is range of x value? Is the volume increasing, decreasing? Well, that comes from our point that we created, right? The volume increases up until we get to 2.039, and then the volume decreases after that point. So it increases on x is less than 2.039, and it decreases on x being greater than 2.039. Well, up until a point, right? So at what point does it stop decreasing? So when we look at this, right, the function eventually does stop decreasing when it hits around 6.295. Once it hits 6.295, it starts to increase again. So let's fix that. So it decreases on, um, so what I'll do is I'll erase this part here and I'll just kind of fix this. So it increases on 2.039 less than x, which is less than about 6.295. So in that area, it's going to decrease. But if x is less than 2.039 or x is greater than 6.295, the function is going to increase. What about exactly at those points? It's doing neither. It's flat. Okay. All right, so a little bit of a summary here. Again, whether you have 3 inches by 8 inches, or whether you have 11 by 14, 11 by 17, 26 by 30, whatever paper you have, the volume function is going to look a little something like this. Okay, and you notice that because of the cutout, the way that we use the cutouts on this, the volume formulas will always have this minus 2x as a part of it, multiplied by x. So that becomes common value for this. So anytime that you want to use a different size paper to make a box, you just replace the 3 and the 8 with whatever numbers you want, but everything else would stay the same. Um, this is one example of a polynomial. And here's a graph, again, just a little bit of a graph of, again, just another example. They use a 3 by 8 paper, and it turns out the best they can get from a 3 by 8 paper is about 7.4 cubic inches. Interesting. Um, and just like before, the smaller side is 3 inches, so the domain's only going to go up to 1.5 because that's half of the 3 inches. Okay, and there we go. So, this is a quick little introduction involving polynomials and what we call relative max and relative min. Um, and just a little bit about how we're going to use these functions, how they look. Different polynomials look completely different, and you'll see a bunch as we go through. There you go. Hope you have a good night. Take care.